Hello and welcome to another episode of Rustacean Station. I'm your host, Alan Wyma. Today I'm with Nick Mathewson, who is a senior developer on the Tor project, or should I say Tor network? Not Tor network, but it should be Tor project, right? Because it's many projects underneath it. Okay, save myself. Yeah, why don't I just take it over to you, because we just chatted for just a few minutes and I already find you to be quite interesting in what your involvement is with Tor. So maybe you can intro yourself and talk a little bit about what is Tor. Go ahead.
Sure. My name is Nick. I've been programming stuff for ages. These days, I mostly spend my time on the Tor project. We make software that implements a network called Tor that provides privacy on the internet in a way beyond what you would get from most encryption tools. Encryption can hide what you're saying to who, but encryption, like TLS, for example, doesn't hide who's talking to whom. And that can be quite sensitive in itself. If you're talking to a doctor who specializes in a certain kind of treatment, you might not, even if someone can't see what symptoms you're describing, the fact that you're talking to them at all may be personal information that you don't want to share. So with Tor, we provide a piece of software that can be run by a large number of volunteers around the world who together provide the Tor network, which clients use to relay their traffic through multiple encrypting hops, thereby anonymizing it to whomever they're talking to. You can download Tor today and use it with the Tor Browser software that's a forked version of Firefox and browse around relatively anonymously.
So that's pretty interesting. So you're saying, so let's just kind of step back for a moment so I can make sure that I understand this. If I use HTTPS, which is kind of the default encryption and kind of this de facto, like that will make my data between whichever server I'm using encrypted, right? Anybody cannot see that data, but they can see me talking to a very specific server, right? So you're saying that Tor actually will encrypt the end-to-end, like who's actually receiving which data. Is that right?
Right. The idea is that you build a multi-hop encrypted path through the network where your client shares a session key separately with each step along the path. So you have, say, a 3-hop path where your client shares a key with the first hop and a key with the second hop and a key with the third hop. And each one of those hops can remove or add only its own layer of encryption. So you send a message out, the first hop removes some encryption, the second hop removes some encryption, the third hop removes some encryption, and only the third hop gets to see who you're talking to. But by the time your message gets to the third hop, it doesn't see where the message came from in the first place. It only sees the hop immediately before it.
So, okay, when you're saying hop, you're saying like an individual server in between, right? So
yes.
I just want to make this very clear for the audience. I think my question is like, is it always 3 hops, or can I maybe add more hops so I can feel better, or remove some so maybe it's a little bit faster?
We have settled on 3 hops for a long time. The main reason for not going higher than 3 hops is this. There is a viable attack against this type of low latency anonymity system called a end traffic correlation attack. And it sounds a little fancy, but all it means is that if the same adversary is observing both ends of the communication, and they do that for long enough, they can match up patterns in the timing and volume of the traffic that you send. There are defenses against this kind of thing known in the literature, and have been since the 80s. Unfortunately, most of these defenses are unrealistic to deploy. You could, for instance, introduce so much latency that all of your messages would take like an hour to arrive. This would maybe be okay for email, but not so good for web browsing or video chat or whatever. Similarly, you could require that everyone using the system always be sending at the same traffic volume all the time. But that turns out not to make ISPs very happy, and it fails in realistic scenarios where people's internets go down sometime. So there are promising research directions for trying to resist correlation attacks like this by introducing only a little bit of dummy traffic. or introducing only a little bit of message delay. I think these are promising, but they haven't yet got to the point where they're so solid that we would say correlation attacks are defeated. Now, with that in mind, if the impact of a correlation attack is that any adversary who sees both ends of the communication can match up timing and volume, adding more hops in the middle doesn't actually make you more secure. Because if the adversary is the first hop and the last hop, they win, even if there's 10 hops in the middle, according to this attack, until, finally somebody manages to figure out ways around it.
Okay, that's pretty interesting. To me, I'm just thinking that you could just introduce some couple of milliseconds or microseconds of latency here and there, kind of throttle up and down depending, and that would kind of make some confusion, but maybe I'm wrong in my thinking.
You get some confusion. One of the problems is, though, you're talking about adding some noise to a signal in order to make the signal harder to detect. And it turns out that extracting signal from noise is something that information processing algorithms can be really good at. It seems, if you look at systems like mixed networks, like people would build in the 1990s a lot, the Cypherpunks remailer, the Mixmaster remailer, those worked by introducing not just a few milliseconds here and there delays, but they focused on emails. So they managed to get randomized delays on the order of minutes to hours. And because of that, it wasn't easy to predict what, if given a message entering the network, when it would leave the network. And that might be okay for email, but it's not okay for most applications.
Okay, so when I'm sending my data across, I'm actually getting every piece of whole data. There's no extra noise like you mentioned before that can throw things. It's just basically 3 hops, and every piece of data that I'm sending out is strictly data. There's no extra noise to try to cause some confusion or something. Is that correct?
Well, there is a little padding support. We're experimenting with different padding algorithms. If anyone who's interested should Google into, I think padding machine is the term that we've been using for research on this kind of stuff, but it's still very much in a research phase. We found padding machines that slow down certain kinds of fingerprinting attacks, but I don't believe we yet have one that's effective in the general case. Hopefully, though, with the transition to Rust, it'll be a lot easier to implement this kind of thing and try out more experiments to try to bring stronger privacy to the internet.
So that's pretty interesting, right? I have to break on this point because, of course, this is a podcast all about Rust. And so, why is it that we cannot do this kind of stuff with C and C++? Because when I talk with seasoned C developers who don't really know too much about Rust, they kind of say, okay, we have smart pointers in C++. I forgot which version that was. We don't really need this kind of stuff. And now you're telling me that with Rust, it's actually going to be able to help you experiment more, if I understood what your comment was. Why is that? Or did I get my comment wrong?
Well, yes, C is indeed a Turing universal programming language. So any program that can be written in C. But I've got a lot of experience using C. We have a lot of experience institutionally using C for this stuff. Currently, the main Tor implementation is written in C and has been since 2002 or 2003-ish. But the implementation is showing its age, and the C language is kind of showing its age for this kind of application. We need something that can handle pretty low-level operations, because we need to be able to really fine-tune the cryptographic implementations to make sure they're fast. We need low-level access to our networking implementations, because we found that there's some stuff that you need to do interacting with the kernel to look at TCP window sizes in order to be efficient about multiplexing user data at the server level. And that stuff is possible in a systems language like C. But you also want to do high-level things like be able to change your padding algorithms a lot, look at different ways to choose paths through the network. And for that, it would be pretty convenient to have a more high-level language. So I think we could steer on ahead just using C indefinitely, but I don't think that's the right choice because, C really does have a lot of gotchas. Even after decades of C experience, I'm still kind of frightened to write tricky C code that works with interesting data structures and passes data around in interesting ways. I'm worried when I have to do anything that deals with the kind of ownership problems that Rust makes it trivial to solve. And I'm really scared when I have to review other people's C code and try to help it be error free, because that can be even harder than writing code in the first place, is trying to figure out what kind of mistakes might someone else have made. And we still make mistakes in C. Around 2016, I believe, we started tracking all of our security bugs in the main Tor implementation just to see, all right, let's just keep account of all of them. Let's track them separately and do regular retrospectives on them. And looking back over that time period, something like around 50%, maybe 50, 60% of those bugs are bugs that would not occur in Rust or in an appropriate dialect of C++ where you forbade null. A lot of them would also not happen. But Rust seems like a much better proposition for us in terms of being safe by default, in terms of not inheriting so many gotchas from C, and in terms of having, a really powerful language that can also go as low level as it needs to.
Yeah, I mean, that's pretty interesting. It makes a lot of sense. Like, I don't know, I just feel like kind of scary with C, right? And the fact that you're a guy who works on encryption and that you feel worried too, that really makes me more concerned, because actually if I understand correctly, the work that you guys do, part of your customers are people who are really trying to get some information out. And if people find out who the people are talking to, they can get killed, I think, right? I mean, I believe some of the people that you guys serve is like reporters and things like that. Yeah. And I'm thinking recently, like they have these like bugs with, I forgot the name of the Israeli company that has an exploit for Mac OS and some other stuff that they were able to like kind of find some people. Like that's super scary. Like, yeah, I mean, this is a huge problem. So how do you like manage to really calm yourself down and like really check this kind of stuff? Are you using like Valgrind or some kind of special tool to kind of help yourself out?
So you're talking about the C side of it. There's a lot of stuff that we try to do in order to keep things from getting out of hand in C, but I don't think any of them are a complete answer. We use static analysis. We turn on all of the compiler warnings that aren't completely bogus. We try to make sure that all of our tests work fine with all of the sanitizers turned on. We do fuzzing for our parser code. We do all kinds of stuff. We do lots of code review. And even then, that's not enough to catch everything in C. We haven't had like a remote code execution vulnerability like in ages and ages and ages. But there's still remote crashes. And remote crashes can be dangerous for what we're doing because, if you suspect that somebody is doing a communication, like you suspect someone's doing a broadcast, if you can cause them to crash, that can give you a way to confirm, okay, is this the person that I suspected or not? So, or if someone is doing two activities at once and you're like watching one of them, like they're chatting in IRC over two different channels at the same time, and you can crash them via one, then, see if they go off the other one and link their activities that way. Even like remote assertion failures are security relevant and they can be quite bad.
Now, if you were to start changing things from C to Rust, I know that would take a long time. The question is going to be, how much safer would you feel and how much better would the runtime be? Would it actually solve all of your security issues? Or what are you kind of thinking?
No, there's still 30 to 40% that would still be present, where we're using Rust. Although, we'll find out because we actually are rewriting in Rust. So just a brief timeline. 7 years ago, we got our first random anonymous user on our bug tracker saying, you should rewrite everything in Rust. And we told them, yes, you're very nice, but we're busy. As usual, that never works. Then a while after that, we started actually really looking into Rust. And that's kind of why we keep going back to that one user. Because maybe they were right.
So you're saying that it was a troll? A troll came in and you guys, or you think it was an actual serious person?
I believe they were serious, but I think they also underestimated the effort involved. I think a lot of the time people think that the hard part in software development is having a good idea rather than executing it. And, they think that they will help by showing up with a good idea that's very hard to execute on. I don't think this person was trolling. I think they were really interested in helping. But anyway, eventually we looked at, well, can we replace parts of the C Tor implementation with Rust? And we tried that for a bit, but it might work well for another program. But our existing C implementation has been hacked on by a lot of people over the years. And, I'm not going to blame anyone but myself, but the overall structure is not very well separated. Like, the parts that would be easy to replace with Rust are the parts that are already the most unentangled from the rest of the spaghetti. And the places where you'd really start seeing benefits are places where, that would be hardest to replace, like replacing the core network loop, replacing, the actual ways we handle I/O deep inside. And that's kind of why I decided, hey, I was still interested in learning Rust and interested in working with Rust, but our internal efforts to, get Tor into Rust piece by piece had kind of stalled because of that. As a hobby, I decided, well, I want to learn Rust anyway because it looks pretty cool. And I wanted a project. And, since I've been doing this for almost 20 years now, I thought, well, maybe a little Tor implementation in Rust just to see how far it goes. And I was doing it, an hour here, an hour there on weekends. At one point in 2020, I took a month off from work though, and spent a lot of that time getting really serious about, all right, can I make this work? Can I get it to work? And, when I was back, I was able to connect to the Tor network and actually send traffic. And that's kind of when, and I took it to the rest of the company, and they were like, hey, this might actually be a good direction forward. Because all the programmers who have been working on CTOR are pretty excited about eventually migrating to Rust instead. I'm not the only person who's just really tired of all of the dangerousness and pitfalls in C. And by moving to Rust, we've effectively got multi-threading for free. And our implementation gets, we haven't done deep performance testing, but our performance right now is comparable to the C implementation. So far, it's only a client, and it doesn't have all of the features of the C client. But, eventually our long-term plan is to just replace the whole thing with Rust and move ahead that way.
You're 100% confirmed that you want to replace all of at least the Tor client with Rust?
The client, yes. And we'd like to do the servers too, because high-performance, high-security servers are pretty well suited to the Rust world. Our existing C server code is also, it shares a lot of code in common with the client code. So once you've got a client, you're not that far away from a server. And what's more, it'll really benefit from things that Rust makes easier, like fearless concurrency, as they say.
So I have another question too, because I always hear, not always hear, but sometimes hear basically talk between Zig and Rust. Have you ever taken a look at Zig?
I have taken a look at Zig. I like Zig a lot. I'm currently, I know Rust way better though. I wouldn't call myself more than a novice in Zig. So I can't really say anything very authoritative about it. Their build system looks absolutely stunning, and I would totally advise anybody else to check it out. But beyond that, I can't really say too much about Zig.
I mean, I'm kind of curious about somebody who's played around with Zig and is really into Rust and has done C. Can you give some kind of comparison? Like if you were to talk to people and say, listen, Rust is kind of like a safe kind of version of running C, even with concurrency. How would you kind of intro Zig to people?
I don't think I know enough Zig to be comfortable doing that right now. Ask me again in a year.
Okay, maybe I will, because I would love to hear more about Zig. And I hear people who really love Zig don't like Rust, which is kind of interesting. I don't know what the difference is to me. I always hear that Zig is kind of like really a replacement for C or an extension to it or something like that. I forgot what the terminology that they used is. All right, sorry for the side chat. I was just curious since you took a look at it.
Only the tiniest bit.
Yeah, but if anything you can give, it would be good, because I haven't had a moment to take a look at it. What I am interested more in I would like to go back to kind of more about what Tor is.
Mm-hmm.
So it's encrypting the traffic end to end, right? So where is that on the network stack, right? You have application layer, you have all these different layers. It's really deep down into the network layer, right?
So it doesn't fit into the standard layering model exactly well. Semantically, it's transferring data streams, sort of like TCP does, but it uses TLS and TCP as a lower layer. So you could consider it sitting above there. It doesn't do like raw IP packets, because doing raw IP packets would expose like the details of your own TCP stack to the opposite end of the network, and that would reveal all kinds of information about your computer. So we don't do that. Also, nobody wants to have we were starting in the early 2000s, and nobody wants to expose like everybody's buggy TCP implementation from then to, who knows what on the opposite side of the internet. So yeah, you can think of it as like a bit below application, a bit above TCP, but it's providing similar semantics in terms of what you send from point A to point B. So the implementation that we're doing in Rust is called ARTI, ARTI. And if you like write a program to use it because it works as a library as well as a proxy, then it's pretty much a drop-in replacement for your TCP connections. Instead of like using StudNet or Tokyo IO or async std IO to get your TCP streams, you get yourself an RD client, and then you ask that RD client to get you a stream over Tor to wherever you're going. And you can layer TLS over that or whatever else your application needs.
Okay, and like what's like the history of Tor? Because as we talked before the show, I understood that it kind of came from the Navy, but you also were in the very beginning of Tor at some point. So could you mind to kind of give a little bit more history about where it came from, why was it developed, and what's it really being used for nowadays?
Sure, that's a lot of questions. So in the mid-90s, there were 3 researchers at the Naval Research Lab. And the Naval Research Lab is a large U.S. institution that's part of the U.S. Navy that includes everything from weapons development, which these guys were not, and pure mathematics, all the way over to pure mathematics. These 3 researchers were in a carpool together. Their names were Syverson, Reed, and Goldschlag. And they started thinking on their carpools, hey, is there maybe some way to actually resist traffic analysis on the internet? Because the internet is starting to get really widely used. And they came up with a design that they called onion routing, based on the analogy of peeling layers of an onion or adding on layers of an onion. And they designed the general idea of how it should work. They worked through the cryptography, and they published a few academic papers in the 90s and early 2000s about it. There were internal implementations at the Naval Research Lab that were not all that widely deployed. I've never actually seen the code for them. But anyway, in the early 2000s, around, I want to say 2002-ish, I was at a internet startup that was working on unrelated junk with my friend Roger Dingledine, and the startup was not doing so well. Roger was spending a lot of his time going to conferences about privacy technology. There he met Paul Syverson from the Naval Research Labs, and he found out that Paul had a problem, which was that he had a research grant to try to build a improved version of onion routing, and he did not have a programmer who would work on it. And their first couple efforts to get programmers internally had not produced successful software for them. So Roger said, hey, I'm really unemployed at this startup right now, and they're about to lay me off because they don't have enough work for me. I bet you could give them the money and tell them just to put me on this and have it be free open source software. And that way I could keep my health insurance and still consult for them when they needed somebody for security. So this complicated arrangement worked out. In the end, I kind of got roped into doing this too because I thought it was pretty neat. The startup folded, but this onion routing project went on. We were working as, I believe, subcontractors originally. Then we were looking for research grants wherever we could get them. Once Tor was open source, that was our implementation. It did not use any code from the Navy. It was based mainly on a onion routing implementation by Made Pfeiffer, who at the time was a graduate student and did a GPL implementation of onion routing. The NRL was not so big on GPL at the time. We negotiated with Mate to get his permission to release our derived work under 3BSD in exchange for actually promising to keep releasing it indefinitely, which we wanted to do anyway, because closed source security software just is no fun and no good and not very secure. So after a while, our research grants that we were on at first dried up. We got funding for a year from the EFF to try to, keep us in business and ramp stuff up. I think the EFF has always been really interested not only in the existence of positive technology like Tor, but in making sure that technology that does things like Tor that needs to remain legal is done well and provided well to the world. And they were pretty interested in keeping us going there. And then one thing led to another. We incorporated as a nonprofit in 2006, and we've been working on Tor ever since.
So where's most of the funding for Tor coming by? Because it is pretty much a free service, right? So how do you guys actually stay in business?
We are still a nonprofit, so we don't have to pay taxes, and that's good. And, people can donate to us and write it off on their taxes in many countries, including the US. But our donations are a mix of research grants, some from the US government, some from other governments, and grant money from individual donors, and money from foundations. Right now, our work on implementing ARTI, that is Tor in Rust, is currently being funded for its first year by the Zcash Major Grants Foundation. ZOMG is their acronym.
Okay. I didn't know the governments were still sponsoring you guys. That's good. The EFF is not sponsoring you anymore?
No, we're still very good friends with EFF, but they found that their fundraising apparatus is a lot better at raising funds for the kind of stuff they do than for the kind of stuff we do. We've had to raise money for grants for a long time. And given the EFFs needing to be a lot more arm's length from governments around the world, that made government grants not really something that they could pursue for us. But we're doing pretty much okay. The pandemic hit pretty hard. Individual donations fell off really hard at the start of the pandemic, and we did have to lay some people off. But we've mostly grown back to the size that we were before the pandemic started. And I think the next few years are going to be pretty impressive in terms of how much software we can make.
I would like to kind of talk more about the onion kind of idea, right? So what I know about TCP is that you have an IP address you want to get to. I'm here, the IP is over there. Somehow there's a routing table which can route your packets around. Because what I understand, let me know if I got this wrong, right, is that, of course, we have this onion idea where we have multiple layers, right? Mm-hmm. So how do I lock these layers in? Although, it could go from this server to that one to that. The hops are not always the same for every single packet, right? So how does this whole onion thing work at a high level that I can somehow wrap everything and get everything there properly? Does my question make sense?
Sure. There's two modes. One of them is easy to explain, and one of them is a bit harder to explain without diagrams. So I'll start with the more straightforward one. Say you want to visit a website over Tor. This is just a regular website on the internet, and you want to visit it over Tor anonymously. So you have a Tor client running on your behalf locally. If it's the most common way to do it, this will be running as a TCP proxy for you locally. It has a list of all of the servers on the Tor network, and it selects servers to make a path for you. It does this according to some rules, trying to not use multiple servers that are run by the same party, trying to choose servers with reasonably high available bandwidth, and stuff like that. And of course, making sure that the final server actually allows connections to where you're going, because some servers don't allow leaving the network. Some servers only support relaying traffic within the Tor network. But once your client has picked the path, it opens a TLS connection to the first relay on the path. And it does a little negotiation. It establishes a secure connection. Then it tells that relay, hey, here is the first half of a cryptographic handshake with the second hop. I want this second hop. And the first relay sees whether it already has a connection to that second hop. If it doesn't, it opens one, and multiple client stuff can get sent over the same TCP connection that way. And then it says, hey, it says to the second hop, hey, here's a client here to talk to you. I'm not going to tell you who they are, but they gave me this cryptographic handshake. And the second hop says, okay, well, here's a cryptographic handshake for them. Now, this is the server's side of this handshake is authenticated to the server. So you don't need to worry that the first hop is secretly impersonating the second one or giving the handshake to someone else. But once this process is done, now the client and the first hop share the keys that they established at the beginning, and the client and the second hop share the keys that they just established by sending messages through the first hop. So from now on, you can send messages to the second hop by encrypting them with the second hop's key, then encrypting them with the first hop's key, and giving them to the first hop. The first hop removes a layer, the second hop removes a layer and gets it. And the reverse path is similar. The second hop adds a layer of encryption. The first hop adds a layer of encryption, takes it back to you, and you've got the right keys to take off both of those. And getting to the third hop is similar. You use that multi-layer channel to tell the second hop, hey, I want to extend to this choice of third hop. Here's the first half of a cryptographic handshake for them. And the second hop opens a channel to the third hop, passes along your handshake, gets a response, and passes that response back, encrypts that response, passes that response back to the first hop, which encrypts it again and gives it to you. You do all the decryption, you see what the third hop said back to you, and that finishes the handshake. Now you know that you share a set of keys with the third hop, and you can use that just to send messages back and forth to the third hop, as you did before with the second hop. So now you want to connect to, say, the Rust website because you want to learn more about everybody's favorite programming language. And so you say to the third hop, hey, please open a connection to rustlang.org port 443. And let's say it's successful. It opens up a TCP connection to the Rust website. It says, okay, that's successful. And it sends you back, yep, you've got a connection. Feel free to send data. And you can send data along to the third hop, which repackages it as TCP for the Rust website. And the Rust website will send stuff back to the third hop. From the website's perspective, it's getting a connection from one of those Tor servers. But from your client's perspective, it's just talking to a local proxy. Now, in fact, it's a little more complicated than this because multiple streams are multiplexed over a single circuit of this type. Like you wouldn't want to have to do a multi-hop cryptographic negotiation for every single TCP connection you open. So there is a certain amount of multiplexing going on. But that's the general summary of how it all works.
Okay, so is it like if I'm going to connect over a WebSocket to a specific server, is it that every request will do this process so that every time once that connection is done, then I need to do the whole process of setting everything up again? Or is there something that's saved for like a session for like an hour or something?
So it's actually a little more clever than that. So these multi-hop paths, we call them circuits. Once they're established, the client holds onto them for a while and reuses them for similar traffic. Now, you don't want to put all of your traffic over. So if you're downloading a web page, say, you would want like all of the embedded resources and all of the JavaScript, all of the links, all to get fetched over the same circuit, probably. But even if you're doing something else at the same time, you wouldn't necessarily want that to go over the same circuit. Like if you're visiting two different websites, you might not want the last hop, the one that we call the exit server. You wouldn't want that last hop to say, hey, the same person who's visiting this website is visiting that website. Or you wouldn't want them to know, like, if you had a long-term, say, IRC connection or some other chat protocol, you wouldn't necessarily want that sharing the same exit with all the websites you're going to because, you might identify yourself on one connection, which is your choice, but not want to have yourself identified on all of the connections at the same time. So what we do is we use some heuristics and we allow the application to signal to us what should be able to share a circuit and what shouldn't. The rule that the Tor browser uses is, generally speaking, a single page load event gets a circuit. So when you type in the address bar in a new tab, that's a new circuit. When you get a completely new page, that's a new circuit. When you go to a new first-party origin. That's a new circuit. I'm probably getting this slightly wrong because I don't know as much on the browser side as the people who work on the browser stuff. I'm very, very low level.
Now, does Tor only work over TCP or does it work over UDP? And also, if it does work over TCP only, what about like long-lived connections like a WebSocket? If I understand correctly, that's actually using TCP underneath.
Mm-hmm. You can do WebSockets over Tor. That should work. We don't currently support UDP over Tor, but we probably will by the end of 2022 because we are looking into ways to expand it to more kinds of traffic. It won't be enough to make it suitable for lossy TCP stuff. Like if you're actually relying on UDP for being an out of order, unreliable transport, we probably won't be able to give you that, but we'll be able to give you basic, UDP over Tor, hopefully this year. The reason you might not want a unreliable transport over Tor is that once you give relays the ability to drop traffic, that enables a kind of attack where a relay selectively drops traffic in order to generate a pattern that's visible on the other side of the network. Like by choosing which UDP packets to drop, it could send a message about who you are. So we don't have a solution for that. So our initial UDP support is going to be semantically reliable in order. So you won't get the unreliability of UDP that allows its efficiency, but you will at least get compatibility with UDP-based protocols.
Now, okay, so this will also protect, I was just thinking about in my head, one of the big things that came out in Firefox somewhat recently is DNS over HTTPS. Like this will also be totally encrypted, right?
Mm-hmm.
When you go end-to-end using Tor.
Yeah, we already do our DNS. So DNS is a special case that we do at the exit. And yeah, you can totally do DNS over HTTPS over Tor. Works fine.
We keep talking about like web browsing, right? We're not really limited to web browsing. If it uses TCP, we could use Tor. Is that correct?
Yes. Now, that doesn't mean that you automatically get privacy for nothing, though. Like, it doesn't mean you can just point your application at a Tor proxy and you're done. The more complex the application is, the more likely it is that it's doing something that makes users look different from each other so that they will stand out from each other on the other side of the connection, or that it has some feature that enables it to like launch some other application that won't necessarily be anonymized, or it has some privacy issue that needs to get really thought through in order to get the privacy right. So a web browser is one of the most complex cases. There are lots and lots of ways to identify people with web browsers. Like it's shocking how few people have exactly the same set of fonts, for instance, or the Tor browser has to do stuff to hide your window size because browser window size also tends to make users look very different from one another. And that information is available over HTTP. But of course, you can't hide it completely or else you get a really bad user experience because pages don't render right. It's a different challenge for different kinds of application. Some stuff is easier than others to anonymize that way. But I'm hoping that with RD, the Rust implementation, getting more and more advanced, it'll be a basis that people can use to make more privacy in their applications. The C implementation was written to be a proxy and has never been very embeddable. The Rust implementation, RD, is meant to be embeddable from day one. And right now, what we're really looking for most is feedback on our API design. Pretty soon, we're going to hit version 0.1. Once we do that, we're going to not make gratuitous API changes. So we're trying to get all of the API feedback we can right now for people who want to embed RD in order to get a Tor solution for their applications.
I just want to ask one last question about Tor before we move on more about the Rust stuff inside of RD. My last question is like, you keep talking about the Tor browser, right? But we also said that you could just run a proxy and then we can point our apps to use that proxy and we kind of get Tor working, mostly to a certain extent, right?
Right.
So what's the difference between if I should use Tor or not, the Tor browser or not, right? Because from my understanding, like I played a long time ago where I was interested in what was on the dark web and I just popped open Tor, popped open the web browser just to take a look to see what's going on. Mm-hmm. And like, my question was like, why should I use Tor browser rather than just use like any browser and then just point it to a proxy?
So I'm only going to be able to give a few examples of this, but there are lots of ways that a regular browser will leak information about you and will generally make it possible for a website to de-anonymize you. For starters, a regular web browser won't be able to do that thing about sending separate traffic over separate circuits. It's going to send all your stuff over whatever circuit is the most recent one, because it won't know to signal to Tor, hey, this image goes with this page, this image goes with that page. So different websites you're visiting are probably going to be able to link your activities to one another, which if they share advertising networks with each other, which a lot of them do, that takes it from theoretical to actual. Like they will, in fact, be able to notice, hey, it's the same person. Similarly, there's also what's called a fingerprint about your browsers, stuff that your browser does that's different from everybody else's. Like there's the set of fonts it uses, which are exposed. There's the window size, which is exposed. And there are dozens and dozens of other things that make individual browsers very distinct. So, somebody who sees you visiting one thing is going to see you visiting other stuff too. And they can probably recognize you from non-anonymous connections you make because your browser will be sending the same fingerprint in that case. Also, there's lots of bypass attacks in browsers, like proxy bypass. Like if you click on a link that opens a video conferencing application, for instance, a lot of people have Zoom or whatever, then Tor Browser will go, hang on, this isn't something I know how to anonymize. Let's double check you really want to do this. But your regular browser will just go, yeah, okay. Or to some applications, not necessarily all of them, but enough of them that you can't really be sure, will they all use the proxy that's configured, or will some of them bypass the proxy and go directly? So, if you would like more than trivial privacy, probably your best bet at this point is Tor Browser or a similar solution. We're moving towards a more VPN-style approach where we have something that can sit in between all of your applications and the network. But that's at least a couple of years off, and it's going to depend on getting a Rust implementation together, because taking a C implementation that was first written as a proxy and then trying to lower it down the stack level is not a position that we want to be in at all.
Okay, maybe I just have one last question, like as somebody who's been working on Tor and really into this field. If you were to advise people, like what would be a good way to kind of remain anonymous online, like their setup, like is Tor enough, or should I add a VPN in? Should I make sure I'm always using HTTPS? Like should I use Tor Browser? Like it's a really open kind of question. Like what would you recommend people do? Because I've heard some people just use like curl to browse the web, which is not ideal, I think.
So this is a bigger question than I can cover in a podcast. And I know there are some links that are really good for presenting this information, both from people who are kind of new to it or all the way up to people who have really high security needs. I'd say like the first thing I'd say is, get a good password manager for your security. Tor Browser can be a good part of your security, but it's not going to magically solve all of your issues. Can we add little links at the bottom of the episode description to stuff? Can I send you a couple of links afterwards?
Yeah, we have the question sheet I shared to you, so feel free to drop links on there and I'll do my best to make sure it gets output.
Cool. I will be able to do that sometime in the next 24 hours.
Yeah, I really appreciate it because I think this is a great topic to give to people. People, especially nowadays, especially with Snowden and everything, everybody's kind of nervous. But then there's always you have to give something or to get something, right? Facebook doesn't come for free. You're giving up some of your data to get some type of value back, right? So, but people kind of want to remain somewhat anonymous to a certain extent. So it's good to hear from somebody who has been in this field for a while, like what your recommendations are. So yeah, we can get back to Artie, right? So I'm just take a look at your dependencies. You're doing some pretty interesting stuff. So you are using Anyhow, which I've heard good and bad. Like I've heard people say you should roll your own, and then I heard people say Anyhow is good enough because there was kind of a lot of, what do you call that? Not friction, but a lot of changing, right? It's like people are using this error or something, and then they went to Anyhow, and then there's also error, EYRE. I see you using Clap, which is interesting too. Tokyo. Go ahead. Maybe you can talk more about your tech stack, why you chose certain things. That's interesting.
We're using Clap and Anyhow at the top level crate, RD. That's the one that implements a proxy, and eventually will implement other command line type stuff too. But once you get to the library layer underneath it, that's the RD client crate. We're not using Clap or Anyhow there anymore. We're trying to keep our errors vaguely generic there. So they're generated with this error right now. I hope sometime in the next couple months we'll have a chance to refactor our errors and have them make a lot more sense, though, because right now they're not terribly user friendly in terms of the hierarchy of how they're made. Like each error is wrapping a different error from a different subcrate. RD is composed of like a whole bunch of different crates. I think like maybe 15 or more right now to just handle the different pieces of the Tor protocol. That might be overkill. I was kind of reacting against our C architecture, which is just a pile of spaghetti and different things calling each other all over the place. Now, in terms of our tech stack, we're trying to be pretty flexible in terms of what we support. We're definitely all in on being an async and futures-based application because we really do need, once this goes server side, to be an event-driven style program. Like a busy Tor server will handle tens of thousands of simultaneous sockets, and doing that with multi-threading is not viable. It's not something we want to get into. So we're doing that with async. We don't force Tokyo. We also support async. We are aiming to also support WebAssemblies at some point down the road. We're doing that based on features. Tokyo is the default, but we want to be able to run pretty much any place that people need us to run. So that's why similarly our TLS is currently provided by the native TLS crate, which wraps your local platform's TLS implementation. But we also want to add support for, again, optional, only pay for what you use support for Rust TLS and whatever else is needed.
Wait, for the WASM, right? Is this for client side or for server side? Because I know with things like Crustlet and things like that, you can actually start running this on a server side, right?
So probably it will mostly be for client, but there is a case to be made for actually running a tiny little server in a web page. In addition to being used for anonymity, Tor is also used for censorship resistance. And one of the things that helps with censorship resistance is letting people spin up tiny little proxy servers on the internet that people can connect to get around oppressive firewalls. One system right now that we're shipping is called Snowflake. It's not written in Rust at all. It's a different team's project, but that uses WebSockets and local Snowflake proxies to help people get around censorship around the world. So being able to run a WebAssembly Tor server would probably be a good piece of a anti-censorship story down the road. But yeah, you're right. For now, the goal of WebAssembly would mainly be just for clients. Also bragging rights.
And actually, I was listening to talking a little bit earlier about the RD client. You're actually using this error and anyhow, at least in your .lock file.
Mm-hmm. Yes.
Is it that you guys switch from this error to anyhow?
No, we're using anyhow at the top level for the command line stuff, and this error for the library level stuff. Any error that another library consumes or another application consumes is typed using this error to make it easier to match and dispatch on it. Whereas once we're above that level of the architecture, we don't worry about exposing stuff to other applications anymore because it's within our own application. And at that level and higher, we just use anyhow. We might change this around in the future. We're not really firmly committed to it.
Now, I'm kind of curious because to me, I thought you would just choose one or the other rather than two different ones. Like, why is it that you're using two different types of error crates or they have totally different meanings? Because I haven't looked so much at these.
Well, I'm not so much a Rust error expert, so I'm going mainly by what folks have told me. My understanding is anyhow is more ergonomic to actually use and write with. Like, you don't need to define your own error type. You can just shove any kind of error type into an anyhow error and just treat them all as one big blob. But anyhow is not easier to consume because of that. Like, if you want to do detection of the actual error type and different application based on that, then you really want a error type that's a enumeration that you could do a match on, that you can do pattern matching on, that you can actually that you can get the data out of by some means other than just formatting that. And yeah, you can downcast with anyhow, but it's less easy than it is to like do pattern matching like you can when your error is in enum. And this error is a tool that helps you define enum based errors. So, it doesn't really tie you to using this error. You could, in theory, move away from this error to something else that would define your error enumerations for you, and the people using your library would never notice.
Okay, so I'm just taking a look over here. It just said that doclog files is very interesting stuff. Most of these I've heard of before, so it's interesting. So you are using libc also, and not using the other one. And this already builds on basically all platforms?
All that I've tried on, it doesn't do WebAssembly yet, like I said, but I've tried it on Windows, Mac, OS X. I know some people have tried it on some of the BSDs, and I know people have like cross-compiled it successfully for iOS and Android. There's a team that has done a stripped-down version of it to use for a contact tracing application for COVID-19 stuff, so that you can like say, hey, am I at risk because of I was in these places, without leaking who you are? And, that's a phone application, and they managed to cross-compile it fine.
Now, this is quite interesting. I just saw this file called want from other crates, right? So this is kind of like a call out for some help.
Yeah, that's a little out of date.
Maybe you can also talk about what this is exactly so people know if they don't come to the project.
So as I was like writing the first implementation of Arty, it's not just me anymore. A lot of other people, some volunteers, some working for the Tor project, have touched it since then. But like when I was just working on it, I really didn't know what was a good dependency, what was a bad dependency. I didn't know very much Rust at all. I was kind of learning as I went. So a lot of stuff I was just looking for, hey, I wish this crate had this feature. I wish that crate had that feature, to generally try to just keep track of like patches I might want to write on other stuff. Most of the stuff that we wanted, that we truly needed, has gotten built. This file used to be a lot bigger. But yeah, there's stuff remaining there that is stuff that it would be kind of neat if it got implemented someday. And, there's stuff that I hope that it gets implemented, or that it gets stabilized in Rust sooner or later, because there's stuff that we're really looking forward to, like being able to write async functions and traits without having to use the async trait crate. We're interested in default implementations and specialized implementations. I think that feature exists, but only in nightly. And we're also interested in existential types, like being able to say, hey, compiler, you figure out the type of the future that we're storing in this variable. And if I understand correctly, all of those are coming down the pipe. So that's pretty good. A lot of these are things that would be neat for someone to work on, but we also have a bug tracker of our own with hopefully fun issues to work on.
And this all compiles with stable Rust, right? Nightly or anything like that?
Yeah, I think currently we support back to Rust 1.53, because we haven't really decided on a minimum supported version policy yet, other than we're not going to break what we support without a good reason.
So some of the newer features that you want to use, though, if they're not supported, you're going to have to provide two implementations, where one is the nice way and two is the not so nice way?
Probably what we'll do is we'll say that the latest version of RD requires a Rust release within the last N months, and then N months after those features get stabilized, we'll be able to start using them. That can be a little frustrating, but it's way better than the situation in the C world, where it was, I think we were in the 2010s before we could finally say, no, we absolutely require C99 support, just because of some holdout compilers that we needed to work for. And we still have issues with the C code with compatibility with different OpenSSL versions and OpenSSL replacements that we run into like 2 or 3 times a year, just because of people keeping their libraries for years and years and years. Compared to that, like supporting the Rust ecosystem back like 9 months to a year is no big deal at all. It's a breath of fresh air by comparison.
So it sounds like you guys are really looking forward to kind of shedding a lot of baggage that kind of came with C, where you have to support all versions of the C standard, basically like a project that's kind of a little bit long in the tooth because it's been around for many, many years and still being used and still is working, where you kind of can come in with some new ideas based on usage and based on working with the code base for some time, right?
And some of that would come from any major rewrite. So I don't want to say like, hey, it's that's something you can only have in Rust, but there are really nice aspects to moving away from some of the technologies. Even though they're technologies we've really learned a lot about over the years. Even I mean, it is hard to write good C, and we are. I don't want to say we're bad at it, but even when you're really good at it, there's a limit to how much complexity you can safely manage and maintain, and the limit in Rust is way higher.
Now, I think I've used up quite a bit of your time. I want to be respectful, but I think there's just one kind of big, or there's a couple of questions I have, and I'll try to make them brief.
Mhm.
I'm really interested as somebody who's been doing C for quite some time, right? Obviously, this is a Rustacean podcast. We want to hear good stuff, but I want to also hear like the bad stuff, right? So somebody who's been using C for a while and really getting into the nitty gritty of it, do you have any things that are not so good about Rust that you say, okay, C does this better or something like that, or maybe another language does it better?
Hmm. I would need some while to think about that. There's little features I want, like specialization and existential types, but I think I would not start a new project in C under most circumstances right now. I would look for ways to do it like either with no standard Rust. Now, new standard support has gotten a lot better since I started writing Rust stuff, but it still has some ways to go there. But I think for this point in its history, I think Rust is doing extremely well. One thing I find that I do, I'm not sure that I miss this, but it is a thing about C. It could just be experience. I'm much more comfortable writing risky, unsafe C than I am writing any unsafe Rust. When I type in that unsafe keyword, I check a whole bunch of references to see what I'm even allowed to do. And usually I decide, I don't think we have like any significant use of unsafe in RD, but even like for a side project, I'll usually decide, no, I'd rather not do it this way. But with C, I really do have thanks to years of standards and descriptions of what implementations are allowed to do, I have a much better sense of like when I'm skirting undefined behavior and when I'm actually doing something that I'm allowed to do. But I think again, this is something that Rust is going to probably work its way through as it does more well-defined semantics work in general.
Okay, that's good to hear. But I'm also looking to hear some really good feedback about, where Rust could be better, because I'm sure there must be places where, like you said, existential types, things like that. There's still things that could be better, are lacking. I mean, when you compare the lifetimes of the two, right? C has a lot more stuff to it, plus many more standards, which probably makes it even worse.
Yeah. I'm not sure this can be done, and certainly it's not like C solves this either, but I would like more robust signals of crate maturity. Like if you wanted to see whether a crate you're thinking of picking up a dependency on is mature, you've got to look at a lot of different signals, like how frequently does the API break? How frequently are the authors still maintaining it? Who depends on it? How many dependencies are there? And it's not like solution to this in C, but in C we found ourselves taking much fewer dependencies than we do now that we have a real package manager. So it's something to think about.
Yeah, and also I think also some feedback from me that you kind of brought up there that you reminded me of. Although there's a package that's been kind of put on crates.io, what I find interesting is that you can still look at the repo. Maybe the last crate was published a year ago, but they're still making updates on GitHub, which is like, okay. So then it's like, well, this is actually being updated, although it looks like it's not because there hasn't been a new release in a while for whatever reason.
Yeah, and that's something to think about as a consumer of that package. Is the reason there have been no updates because like the last version was perfect and the next version will be perfect, and there's no reason to do an intermediate version? Are the maintainers like just having fun and not really planning to put out a release? That's the kind of question you ask sometimes when you see that situation. So, don't get me wrong, there's nothing wrong with like writing software for fun and doing releases on your own schedule. Like if I'm not, paying somebody for their software, I should extend them a tremendous amount of latitude in what kind of support I expect.
Yeah, true. And also sometimes you have to also get in there yourself and kind of make some changes too.
Yeah. And that's actually an area I found like the Rust ecosystem to be a tremendous improvement over what I'm used to in C. Like we get way more patches way more frequently for RD than we do for the C Tor. It could be because it's a new project. It could be because Rust is new and attractive. But I think also part of it is that people don't feel so afraid that they're going to break something if they look at the code funny. Similarly, when I write patches for other Rust crates and other Rust programs, I find that people are much more willing to accept them after some discussion and revision than they ever were in C. And I think part of that could just be culture, part of that, but I think part of that is more safety lets you be more open to contributors that you haven't, really walked with and checked all of their coding practices.
Actually, I have one question that just popped into my head, and I don't know of an easy way to say this, but one thing I've noticed recently is that there seems to be a little bit of a drama happening within Rust for some things. I don't know if they're all tied together. Have you noticed any of this kind of like the Rust moderation team kind of resigned all at once? And then, I don't know, I've always heard of this kind of stuff happening, but like in C, I mean, there's nothing like a central committee where there's lots of drama, I think. At least it's not so in your face. What I have heard of in C is that you do have kind of a lot of companies coming together, the big tech companies, and then them kind of controlling. I don't know if that's true or not. Is there anything similar in the C?
I think C is big enough that the drama is diffuse. There are numerous pits of toxicity in the C ecosystem. I've never been involved with the standards committee, so I can't speak to that. I think that the fact that this administrative and organizational drama is going on with Rust is a good sign that people regard it as a serious project with real needs and the people are actually trying to get Rust going in a good direction. There's definitely C sub-communities or C adjacent sub-communities that have major drama and major dysfunction, and there's no programming syntax or programming environment that can defend against that. But I don't know that much about current situations within the Rust world, but I don't think that they are all that high comparatively on the scale of how much argument and ill will can happen in free and open source software. So I have very high hopes of like Rust as an organization and as a community working their way through their issues.
Yeah, I appreciate your feedback because I'm always kind of interested on how the Sioux world is, because I feel like they're kind of their own. I mean, it's years, right? So they have a kind of a different setup, not to mention it's before the internet days when C came out, right? So it's definitely evolved, I think, and definitely different.
But most of the people you meet who will know C like learn through internet stuff or through internet resources. Like I'm probably like my generation is one of the last who actually learned C before they got web browsers. Like pretty much everybody who's learning C since the mid 90s has been doing it with way better resources than we had back then.
Yeah, I appreciate it. So you came from the old days where you went to Barnes & Noble, picked up a book and really had to go through it, or went to school, right? Dead tree days.
Where I had to carefully explain to my grandparents why what I really wanted was a C compiler for my Commodore 128 and, what that was and why that was a good thing and why it costs $100 in 1980s money, but why it would, just open new worlds to me. And yeah, it was a different time.
Yeah, I can imagine this. I mean, it's interesting how if you can compare then with now, it's like, don't even talk about C compiler, right? Anything in tech, if it's like, I'll pay $900 for an iPhone now is normal for any kind of consumer. But like you said, $100 back then for a C compiler, like it must be extremely alien to anybody who is not doing programming.
Yeah.
I think one last question I have is somebody like who has gotten up and going with you're using basically, I think you said no standard, which would basically be core Rust, right? Using core.
We're not doing no standard in RD. We're definitely using the full standard library and using lots of other stuff. The only times I used like no standard stuff is like for weird little side projects and experimentation.
Okay. But going from C to Rust, like, do you have any kind of tips or tricks you want to give to people about like people who are starting off in Rust, either from scratch or even like from C to Rust? Like what kind of things you'd want to, I seen your eyes get really big for a second. Like, this is, I don't know what your thought was, but.
I'm not so much an educator, but just from my own experience, I'd say like take your time and go slowly. There genuinely is a learning curve about ownership and lifetimes. And there are other things that you may have seen from other languages, but they're going to interact with the bar checker system in ways that you might take a little while to get used to. That's one thing I'd say. Another thing is for your first Rust project, don't pick something that requires a complicated self-referential data structure. Pick something that's easy to express and save the complicated case for once you understand the simple case.
Yeah, I hear that a lot. Like building a linked list in Rust is like one of the most complicated things, especially if you're just beginning out because of just the way the ownership works.
Yeah, and you don't often have to write your own linked list, but if you do, then you might want to not have that be your first project. I'm kind of lucky that when I was writing RD, I started from like the lowest level stuff, which is cryptography and parsing and just grabbing bytes and moving them around, which is very, very straightforward to do, and kind of built towards more difficult stuff. And, by the time I had deal with more complicated structures, I knew my way around the system a bit better.
No, it's very interesting to hear that the low level stuff is actually makes it easier. But I suppose since it's very low level, there's not much logic to it. Just really very raw kind of do this, do that kind of very simple steps, I'm guessing.
Right. The data structures are basically byte slices at the lowest level. And those are much easier to work with than a lot of other stuff.
Okay. Yeah, I don't think I have any other questions. Like, I really appreciate your time. If there's anything, maybe you have some shout outs or something like you want people to come check out Artie or to help out with certain issues or, maybe donate to a charity, any kind of thing you want to give a shout out to.
Yeah, I'm going to send Alan some links next 24 hours or so after this is recorded. And one of them is going to be a link to our repository and issue tracker. Please check out anything you think you might be interested in. No bug too small, no bug too big. And, anything you can help out with, we would love your advice. Even if you're just interested in embedding RD in your own Rust network program, have a look at the API. Let us know what you think, where you would like it to be improved, because now is the time. And we hope our work is useful to you and hope that you're having a good time too out there.
Okay, thank you so much. I'm definitely taking a look at it. I have it popped up in my browser. And I appreciate you kind of explaining to me very simply and clearly, like, what is Tor? Because it's always been in my mind, like, what is it actually doing? I don't get it. And then I read it, but I didn't quite understand it. And I appreciate your explanation. It made it very clear for me.
Thank you. It's been great talking with you.
Thank you again. Maybe we'll have you come back like when Artie's been working for a year or so, like when you're at a 1.0 release or so. I don't know. You reckon like it may take some time.
We'll see.
Yeah, and kind of hear like what's, what postmortem, right? What's the good, what's the bad? If there's any bad, it sounds like things are pretty good. So I'm happy to hear that. Other than that, really, again, thank you for your time. And maybe help you again soon.
Well, thanks.